Welcome! In this session, we'll explore problem number 2201, count artifacts that can be extracted. This problem challenges us to analyze an NXN grid and determine how many artifacts can be fully extracted. It's an engaging exercise that involves careful grid traversal and logical thinking. Let's dive right in. In this problem, the goal is to determine how many artifacts on an NXN grid can be fully extracted. An artifact is defined as a rectangular subgrid, and it can only be extracted if every cell within that rectangle has been uncovered. Initially, the entire grid is covered, and you're provided with a list of cells that have been uncovered. Using this information, you need to check which artifacts can be fully uncovered and return the total count of such artifacts. The input consists of three main components: the integer n, which defines the size of the grid, a list of artifacts where each artifact is represented by its top left and bottom right coordinates, and a list of uncovered cells, each represented by its row and column indices. The output should be a single integer that represents the count of fully extractable artifacts. To better understand the problem, let's look at an example. Here, n is 5, meaning the grid is 5 times 5. We have two artifacts. The first one spans from cell 1, 1 to 2, 2, and the second one spans from 2, 3 to 2, 4. The list of uncovered cells includes 1, 1, 1, 2, 2, 1, 2, 2, and 2, 3. For artifact 0, all its cells 1, 1, 1, 2, 2, 1, and 2, 2 are present in the uncovered cells, so it can be fully extracted. However, for artifact 1, while 2, 3 is uncovered, cell 2, 4 remains covered, meaning it cannot be fully extracted. Therefore, the output is 1, as only one artifact can be fully extracted. Now let's examine another example. This time, the grid size is 3 times 3, and there are two artifacts. The first artifact spans from 0, 0 to 1, 1, and the second spans from 1, 2 to 2, 2. The uncovered cells are 0, 0, 1, 1, and 2, 2. For artifact 0, the required cells are 0, 0, 0, 1, 1, 0, and 1, 1. However, only two of these, 0, 0, and 1, 1, are uncovered, so it cannot be fully extracted. For artifact 1, the required cells are 1, 2, and 2, 2, but only 2, 2 is uncovered. Hence, neither artifact can be extracted, and the output is 0. Finally, let's discuss the constraints and edge cases. The grid size n can range from 1 to 1000, and the number of artifacts and uncovered cells can each go up to 100,000. Each artifact is defined by its top left and bottom right corners, and every dig cell is unique. In edge cases, if there are no artifacts, the output should be 0 regardless of the uncovered cells. Similarly, if no cells are uncovered, no artifacts can be extracted, so the output is also 0. For single-cell artifacts, the artifact can be extracted only if the specific cell is uncovered. Lastly, for large grids with sparse dig cells, the solution should be efficient, ensuring that unnecessary checks are avoided to handle these scenarios within the given constraints. To tackle this problem, we need to determine how many artifacts on an NXN grid can be fully extracted. An artifact is defined by a rectangular region, and it can only be extracted if all of its cells are uncovered. The inputs provided include a list of artifact coordinates and a list of uncovered cells, which we must use to validate each artifact. However, there are key constraints to consider. The grid size can be very large, up to 10,000 by 10,000, which means processing the entire grid explicitly is not feasible. Additionally, both the artifact list and the uncovered cell list could be substantial in size, making naive approaches inefficient. Therefore, we need a strategy that efficiently checks whether all cells of an artifact are uncovered without becoming computationally expensive. One straightforward method is the brute force approach. The intuition here is simple. For each artifact, we can iterate over all the cells it occupies and check whether each cell is present in the list of uncovered cells. To count the number of fully uncovered artifacts, we repeat this process for all artifacts. However, this method has significant drawbacks. Suppose there are m artifacts, and each artifact has an average of s cells. Checking all these cells against a list of k uncovered cells results in a time complexity of O, m*k*s. This is because, for each cell, we would perform a linear search through the uncovered cells list. While this approach is simple to implement, it is highly inefficient for large grids or datasets due to the repeated and costly checks for each cell in the uncovered list. To improve efficiency, we can use an optimized approach based on key observations. The first is that we can pre-process the list of uncovered cells into a set, which allows for constant-time lookups, or O1, queries, for each cell. This eliminates the need for repeated linear searches. Additionally, instead of directly iterating over all artifacts in uncovered cells, we can focus on validating each artifact by checking only its own range of cells against the uncovered set. Importantly, while the grid size itself is large, we don't need to process the entire grid, only the cells relevant to the artifacts in uncovered list. Using this strategy, we pre-process the uncovered cells for fast lookups, then iterate through the rectangular range of each artifact to check if all of its cells are in the uncovered set. If they are, we count the artifact as fully extractable. The complexity of the optimized approach breaks down as follows. Pre-processing the uncovered cells into a set takes k, where k is the number of uncovered cells. Validating the artifacts involves iterating over all m artifacts and checking their s constituent cells, resulting in a time complexity of m*s. Combined, the overall complexity is k plus m*s, which is a significant improvement over the brute force approach. While this method is efficient and scalable for large inputs, there are trade-offs. It requires slightly more memory to store the uncovered cells in a set, and the runtime still depends on the number of cells per artifact. For artifacts with large ranges, this can still add to the processing time. Despite this, the optimized approach is well suited for the problem as it effectively balances time complexity and memory usage, leveraging the constraints to process only relevant cells. Comparing the brute force and optimized approaches highlights why the optimized strategy is preferred. The brute force method has a time complexity of m*k*s and negligible space requirements, making it easy to implement but inefficient for large inputs. On the other hand, the optimized approach reduces the time complexity to k plus m*s by using a hash-based lookup for uncovered cells, though it requires k additional space for pre-processing. The optimized approach is more scalable and efficient, particularly for large datasets, as it avoids unnecessary processing of irrelevant cells. Ultimately, this balance of performance and scalability makes the optimized approach the best choice for solving the problem within the given constraints. To solve this problem, we need to determine how many artifacts in an NXN grid can be fully extracted. An artifact is represented as a rectangular area, defined by its top left and bottom right coordinates. The condition for extraction is that all cells occupied by the artifact must be uncovered. To achieve this, we are given two inputs, a list of artifacts and a list of uncovered cells in the grid. The first step in our algorithm is to parse these inputs. We read the grid dimensions, the artifact coordinates, and the uncovered cells. To optimize performance, we convert the list of uncovered cells into a set. This allows us to perform quick membership checks to verify if a cell is uncovered. For example, in Python, we can construct the set like this: uncovered_set equals set I, j, for I, j in uncovered. This ensures that verifying a cell's presence in the uncovered set takes constant time, which is critical for the efficiency of the upcoming steps. Next, we focus on processing each artifact. For every artifact, identified by its top left and bottom right coordinates, R1, C1, R2, C2, we need to generate all grid cells it occupies. This involves iterating over the rows from R1 to R2 and the columns from C1 to C2. Once we generate these cells, we check if all of them belong to the uncovered_set. To do this, we use nested loops. For each row and column within the artifact's bounds, we verify if the cell exists in the uncovered set. If we find even one cell that is not uncovered, we immediately stop checking further and mark the artifact as not extractable. This early exit reduces unnecessary computations. If all cells are verified to be uncovered, we increment our counter for extractable artifacts. This process ensures that we systematically evaluate each artifact based on the given conditions. After processing all artifacts, we return the total count of fully extractable artifacts. This count represents the number of artifacts for which every occupied cell was found in the set of uncovered cells. The efficiency of this algorithm relies on a few key insights. First, using a set for uncovered cells ensures that membership checks are performed in constant time. This is crucial because the nested loop structure involves multiple such checks. Second, the algorithm minimizes redundant work by breaking out of the loop as soon as we determine that an artifact cannot be extracted. Finally, the algorithm is scalable and optimized for large grids and input sizes, leveraging the fact that artifacts are generally sparse compared to the grid size. These design choices make the solution both efficient and practical. The algorithm uses a few key data structures to achieve its efficiency. First, the set of uncovered cells is critical for fast lookups. By storing these cells in a set, we can verify their presence in constant time, which is especially useful given the nested loop structure for artifact processing. Second, a simple integer counter is used to track the number of extractable artifacts. This counter is updated only when an artifact is found to be fully extractable, making it lightweight in terms of memory usage. Moving on to the complexity analysis, the time complexity of the algorithm is determined by the number of artifacts and the average number of cells each artifact occupies. Constructing the uncovered set takes U, where U is the number of uncovered cells. Checking each artifact involves iterating over its cells, which takes M*k, where M is the number of artifacts and K is the average number of cells per artifact. Combining these, the overall time complexity is U plus M*k. In terms of space complexity, the main contributor is the uncovered_set, which has a size of U, where U is the number of uncovered cells. Apart from this, the algorithm uses a few temporary variables and a counter, which require constant space. Therefore, the overall space complexity is U. To better understand the algorithm, let's walk through an example. Suppose the grid size is 5 × 5, and we are given 3 artifacts with coordinates 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 4, 4. The uncovered cells are 0, 0, 0, 1, 1, 0, 1, 1, 2, 2, 3, 3. First, we convert the uncovered cells into a set, uncovered_set equals 0, 0, 0, 1, 1, 0, 1, 1, 2, 2, 3, 3. Then, we process each artifact to determine if it is fully extractable. For the first artifact, 0, 0, 1, 1, the cells it occupies are 0, 0, 0, 1, 1, 0, and 1, 1. All of these cells are in the uncovered set, so this artifact is extractable. The second artifact, 2, 2, 3, 3, occupies the cells 2, 2, 2, 3, 3, 2, and 3, 3. However, the cells 2, 3, and 3, 2 are missing from the uncovered set, so this artifact is not extractable. The third artifact, 4, 4, 4, 4, occupies the single cell 4, 4, which is also missing from the uncovered set, making it not extractable. Therefore, only the first artifact is extractable, and the algorithm returns a result of 1. Edge cases to consider include scenarios with no artifacts or uncovered cells, artifacts completely outside the uncovered range, and overlapping artifacts. These conditions are handled gracefully by the algorithm, ensuring robustness across different inputs. The provided solution solves the count artifacts that can be extracted problem by iterating through each artifact and checking if all its cells are dug up. First, the dug_cells set is created to store all the cells where digging has occurred, ensuring quick lookups. The extractable_count variable is initialized to 0 to keep track of the number of fully extractable artifacts. For each artifact, the solution extracts its coordinates, top left and bottom right corners. The algorithm then iterates through all rows and columns covered by the artifact, checking if each cell is present in the dug_cell set. If a cell is missing, the all_cells_covered flag is set to false, and the inner loops break early to optimize performance. If all cells of an artifact are uncovered, the extractable_count is increment. Finally, the function returns the count of extractable artifacts after processing all artifacts. This solution runs efficiently in K*M, where K is the number of artifacts and M is the maximum number of cells per artifact. Using a set for dug_cells ensures constant time complexity for membership checks, making the approach suitable for the problem's constraints. Here, we begin by defining our solution in Java. The method count artifacts takes three parameters: the grid size n, a 2D array artifacts, and another 2D array dig representing the cells that have been dug up. First, we create a hash set called dugCells to store all the cells that have been dug. Each cell is represented as a string in the format row, column for easy lookup. We then iterate through the dig array and add each dug cell to this set. Next, we initialize a variable extractable count to 0, which will keep track of the number of artifacts that can be fully extracted. To determine this, we loop through each artifact in the artifacts array. Each artifact is represented by its bounding rectangle, defined by the top left corner, R1, C1, and bottom right corner, R2, C2. For each artifact, we introduce a flag all cells covered and initially set it to true. This flag will help us track whether all the cells within the artifact's bounds have been dug up. Then, we proceed to check each cell within the artifact's rectangle. For each cell within the artifact's bounds, we use nested loops to iterate over the rows and columns. We check if the current cell, represented as row column, exists in the dug cell set. If we find a cell that has not been dug, we set the all cells covered flag to false and break out of the inner loop. This ensures that we stop checking further cells for the current artifact as soon as we know it cannot be fully extracted. After examining all the cells for a given artifact, if the all cells covered flag remains true, it means all the cells required to extract this artifact have been dug. In that case, we increment the extractable count by 1. Finally, after processing all artifacts, we return the extractable count as the result, which represents the total number of artifacts that can be fully extracted based on the given dig operations. This problem challenges us to determine how many artifacts can be fully extracted from a grid, given their positions and the cells that have been dug. Each artifact is defined by its top left and bottom right corners, and all the cells within those boundaries must be dug for the artifact to be considered extractable. To break this down, let's start with a grid of size 5, where we have two artifacts. The first artifact spans horizontally from cell 00 to 01, and the second artifact is a single cell at 101. The cells that have been dug are 00, 01, and 11. First, we'll convert the list of dug cells into a set for quick lookup. This gives us a set of coordinates 00, 01, 11. This setup ensures we can efficiently check whether each cell of an artifact has been dug. Next, we process artifact 1, which spans two cells horizontally, from 00 to 01. We check each cell within this range. The first cell, 00, is found in the dug cell set, and so is the second cell, 01. Since all cells for artifact 1 have been dug, it is extractable, so we increment our extractable count to 1. Now, for artifact 2, which is just a single cell located at 101, we check if this cell is in the set of dug cells. It is, meaning all cells for artifact 2 are dug as well. This makes artifact 2 extractable, so we increment the extractable count again, bringing it to 2. Thus, the final output for this example is 2, as both artifacts can be fully extracted. In the next example, we work with a 3x3 grid and 2 artifacts. The first artifact spans a 2x2 square from 00 to 11, and the second artifact is a vertical line from 12 to 22. The dug cells are 00, 01, 10, and 22. We begin by converting the list of dug cells into a set for efficient lookup, resulting in the set 00, 01, 10, 22. Starting with artifact 1, we iterate through its cells. The top left cell, 00, is in the dug cell set, as are 01 and 10. However, when we check 11, it is not in the dug cell set. Since not all cells of artifact 1 are dug, it cannot be extracted. For artifact 2, which spans vertically from 12 to 22, we begin checking its cells. The first cell, 12, is not found in the dug cell set, so we immediately stop checking. Without all cells being dug, artifact 2 cannot be extracted either. This means that neither artifact in this example is extractable. The final output is 0, as no artifacts meet the condition of having all their cells dug. In the final example, we work with a 4x4 grid and 2 artifacts. The first artifact spans two cells horizontally, from 00 to 01, while the second artifact forms a 2 by 2 square from 1 1 to 2 2. The dug cells are 0 0 0 1 1 1 1 2 2 1 and 2 2. Converting this to a set gives us 0 0 0 1 1 1 1 2 2 1 2 2. For artifact 1, we check its cells 0 0 and 0 1 and find both in the dug cell set. This means artifact 1 is extractable, so we increment the extractable count to 1. For artifact 2, we check its cells 1 1 1 2 2 1 and 2 2. All these cells are in the dug cell set, so artifact 2 is also extractable. Incrementing the count again brings the total to 2. The final output for this example is 2, as both artifacts can be fully extracted. In this problem, we aim to determine the time complexity of the solution by breaking it down into its fundamental steps. First, we create the dug_cell set, which involves iterating over the dig list. If there are d dug cells, this operation takes O(d) time. Next, we process each artifact, where m represents the number of artifacts in the list. For each artifact, we iterate over all the cells it occupies. If the average number of cells per artifact is k, and the total number of cells across all artifacts does not exceed the grid size of n(2), then the total number of cell checks in the worst case is n². Furthermore, each cell check involves verifying if the cell is part of the dug_cell set, which is an O(1) operation on average for each membership check. Combining these steps, the overall time complexity is O(d) for creating this set and n² for processing the artifacts, resulting in an overall complexity of n², since d cannot exceed the total number of grid cells, n². Now let's analyze the space complexity of the solution. The dug_cell set stores all the dug cells from the dig list, and its size is proportional to the number of dug cells, which is d. Therefore, the space used by dug_cells is O(d). Besides this, the algorithm uses a small number of additional variables, including integer variables like extractable_count, R1, C1, R2, C2, and a Boolean flag all_cells_covered, all of which require O(1) space. Since the space required for the dug_cell set dominates, the overall space complexity of this solution is O(d). To compare, a naive brute force approach might involve explicitly storing all cells in an nxn grid for each artifact and checking each grid cell against the dig list. This would require n² space for the grid and n² *d time, as every dug cell would need to be compared against every artifact's cells. The current solution avoids these inefficiencies by using a set for O(1) membership checks and eliminating the need for explicit grid storage. Let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, all artifacts occupy minimal space, such as a single cell each, and all necessary cells are already dug. Even in this scenario, the algorithm must still iterate over all artifacts and their cells, leading to a time complexity of n². In the average case, artifacts and dig operations are evenly distributed, and the number of cells checked is proportional to the total grid size. The time complexity remains n² here as well. In the worst case, the artifacts cover the entire grid, meaning all n2 cells. Every single cell would need to be checked against the dug_cell set, and the set itself would also contain up to n2 entries. In this scenario, the time complexity is n², and the space complexity is O(d), where d equals n2. To formalize this, the algorithm iterates over all cells in all artifacts, which is bounded by the total number of grid cells, n2. Each cell check is O(1) due to the efficiency of set membership operations. Consequently, the time complexity is n², while the space complexity depends on the size of the dug_cell set, which is at most n², since there are no more than n2 cells in the grid. Let's start by discussing some of the common mistakes that can occur when solving this problem. First, many candidates struggle with interpreting artifact boundaries correctly. An artifact isn't always a perfect square, it can be rectangular, so it's crucial to carefully parse the top left and bottom right corners of each artifact. Misinterpreting these boundaries could lead to miscounting which cells actually belong to an artifact, resulting in incorrect extractions. Another frequent issue is overlooking edge cases. For example, an artifact that's just a single cell needs special handling because its top left and bottom right coordinates are the same. Similarly, artifacts that overlap grid edges can cause errors if not handled properly. Then there's the matter of inefficient cell lookups. Instead of iterating through the grid directly to check uncovered cells, which can be very slow for large grids, it's better to use pre-computed data structures like sets for faster lookups. Lastly, many candidates fail to optimize artifact validation. Instead of redundantly validating all the cells of an artifact repeatedly, a more efficient approach would involve marking uncovered cells in a way that minimizes redundant computations. This is particularly important when artifacts share cells, as redundant validations can quickly add up. Another common pitfall is incorrectly updating the set of uncovered cells. After validating an artifact, it's essential to remove its cells from the uncovered set. Failing to do so can lead to double counting artifacts, which inflates the final count. To address these challenges, there are several key strategies to keep in mind. First, pre-processing the grid to map each artifact to its constituent cells can make validation much more efficient. For instance, representing uncovered cells using a set allows for constant time lookups. When validating artifacts, focus on checking whether all their cells exist in the uncovered set without performing redundant checks. It's also important to be prepared for edge cases during interviews. You might encounter scenarios like artifacts with no uncovered cells, overlapping artifacts, or those that align with grid boundaries, so make sure you can discuss these explicitly. Lastly, always aim to optimize your solution. A time complexity of O(n) squared, or better is ideal, as brute force approaches with O(n) cubed, or worse are unlikely to meet the problem's constraints. This problem also shares similarities with several related problems on LeetCode. For example, LeetCode 200, Number of Islands, involves analyzing connected components within a grid, which is conceptually similar to parsing artifacts. Similarly, in LeetCode 695, Max Area of Island, the focus is on identifying regions within a grid, which parallels the process of identifying artifact boundaries. LeetCode 54, Spiral Matrix, involves traversing grid data in specific patterns, which can help you think about grid-based parsing in a structured way. And in LeetCode 1277, Count Square Submatrices with all ones, you'll encounter efficient boundary checks, which are also important for this problem. There are also alternative approaches to solving the problem. A brute force method involves iterating through every cell and validating artifacts by directly checking all their cells. While simple, this approach is inefficient, with a time complexity of O(n) cubed in the worst case. A more practical alternative is pre-processing with a hash map. By mapping each artifact to its set of cells during pre-processing, you can validate artifacts more efficiently by simply checking if all their cells exist in the uncovered set. This approach trades a bit of extra space for much faster validation, achieving a time complexity of O(n) squared. Another advanced technique you could consider is bit masking. With this approach, you represent the grid as a series of bit masks, where each bit indicates whether a cell is uncovered. This can significantly reduce memory usage because you're storing grid data in a compact format. However, the trade-off is that bit masking increases implementation complexity, as working with bits often requires additional operations to manipulate and interpret the data. Moreover, while bit masking can be highly efficient for smaller grids, it has scalability limitations with very large grids. Therefore, it's important to weigh the memory savings against the added complexity and ensure the approach aligns with the problem's constraints and requirements. Great work completing the problem. Today, we tackled count artifacts that can be extracted and explored ways to analyze and solve grid-based challenges. We reviewed the complexity and key strategies involved. Keep practicing, and you'll master these concepts. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!